In August 1983, an industry adopted a 14-page specification that described almost nothing. No timing model, no file format, no guarantee about what a receiving device would do with anything it was sent. 700 companies implemented it. None of them paid a license fee because there was never one to pay, and the engineer who proposed it never made a cent from it. In 1981, you could own 2 synthesizers and be unable to connect them. Control voltage was not one standard, it was 2. Moog, Roland, Sequential, Oberheim, and ARP used volts per octave. 1 volt equals 1 octave. Korg and Yamaha used hertz per volt, doubling the voltage equals an octave. The MIDI Association's own history states the consequence flatly. Connecting a hertz per volt keyboard to a volts per octave synthesizer will produce sound, but it will be completely out of tune. The proprietary digital systems were worse because they were incompatible in more sophisticated ways. Roland's digital control bus existed on exactly 2 instruments, the Jupiter 8 and the Juno 60. Oberheim used a 37-pin parallel bus across the OBX, OBXA, and OB8. Being parallel, it was genuinely faster than what came next. Remember that. Yamaha had key code on the CS70M and the SK series. From Yamaha's own tutorial page, of course the 2 were incompatible. A detail worth savoring, Roland's DCB had an internal message type, also called key code. 2 companies independently coined the same term for mutually unintelligible things. The obvious reading is deliberate lock-in. I went looking for evidence of that and did not find it. No source I could locate asserts that any manufacturer designed an interface to exclude rivals. The MIDI Association puts the causation the other way around. Fragmentation created customer lock-in, it was parallel evolution. Chicago NAMM, the last week of June 1981, Ikutaro Kakahashi of Roland approached Tom Oberheim about an international standard for synthesizer communication. Oberheim suggested he talk to Dave Smith at Sequential Circuits. Note the direction of that. Roland was the market leader. Its own proprietary bus was 9 months old, and it is the incumbent who initiated and the fragmented periphery who resisted. That is backwards from how standards usually go. Kakahashi had used open publication as a weapon before. In 1966, he published reference books to protect Japanese manufacturers from foreign patents. He understood that the constraint on Roland's growth was not Oberheim's market share. It was the total size of the market. And what suppressed it was that nothing worked with anything. October 1981, the 70th AES convention in New York, Dave Smith and Chet Wood presented preprint 1845, the USI, or Universal Synthesizer Interface. 19.2 kilobaud over quarter-inch phone jacks, point-to-point. The paper says openly that the interface was untested. It was rejected, and the criticism was engineering, not territory. Second Synthesizer Interface Conference, Tokyo, the 24th of October. 3 objections, as the MIDI Association records them. 19.2 kilobits is too slow. Quarter-inch jacks will have ground loop problems, and there is no concept of synchronization or clock. Then they supplied the fixes. Carl Hirano of Yamaha designed the U-art arrangement with photocoupler isolation. Roland proposed the 5-pin DIN connector, already in use on the TR-808, and Tadao Kikumoto of Roland contributed the tempo and clock messages, the status and data byte architecture, and running status. The 2 cleverest efficiency features in MIDI came from Roland, not from Sequential, which complicates the shorthand that Dave Smith invented MIDI. Winter NAMM, Anaheim, February 1982. 12 companies in the room, and it failed. By the MIDI Association's account, it was the American and European manufacturers who couldn't agree. Some wanted expensive, high data rate connectivity. Others didn't see the point of an interface at all. Craig Anderton's history records the specifics. Oberheim feared MIDI was inadequate because his parallel bus was faster, and Dave Rossum of EMU suggested Ethernet. In 1982, an engineer proposed Ethernet for synthesizers. He was technically right and strategically wrong, and that sentence is this entire episode. After the meeting failed, Kakahashi sent a colleague to encourage Dave Smith to keep going. The standard survived because the incumbent with the most to lose refused to let the challenger's proposal die. Smith put the decision on the record himself. We wanted to be sure we had 100% participation, so we decided not to charge any other companies that wanted to use it. Read the reasoning rather than the generosity. That is not idealism, it is an adoption calculation. Total participation was the design goal, and a fee was an obstacle to it. This is not custom, it is contract, and it is still live. Any member holding a patent necessarily infringed by a compliant implementation must license it royalty-free, and the obligation survives leaving the association. One honest correction. Because precision is the point, the specification and the patents are free. The MIDI logo is separately licensed. It is closer to the USB model than to pure openness. The data rate is 31,250 baud. 8 data bits, 1 start, 1 stop, 10 bits per byte, 320 microseconds per byte. The explanation usually given is that the number divides cleanly from a common clock crystal. 1 megahertz over 32 is exactly 31,250. No primary source says so, and it is offered here as unverified. What is documented is duller and better. Roland's DCB already ran at exactly 31.25 kilobaud through an Intel 8251 AI UART. The Japanese proposal that replaced Smith's 19.2 imported the rate Roland had already built silicon around. Then the resolution. Every data value in MIDI is 7 bits, 0 to 127. The reason is structural. Status bytes have the high bit set, data bytes have it clear, so a receiver joining a stream mid-flight can always find the next message boundary. That is what the 8th bit buys. The 128 step limit buys self-synchronizing robustness on a noisy 1982 serial line. It was already tight on day one. The Yamaha DX7, the most successful MIDI instrument ever made, transmitted velocity to a maximum of 100. It used 79% of the available dynamic range from launch. 16 channels for 2 reasons that are both true. It was 8 in the interim spec and raised to 16 by a Roland fax in July 1982. And the channel lives in the low nibble of the status byte, 4 bits, therefore exactly 16. The connector is a 5-pin DIN, and it uses 3 pins, 2 are left unconnected, 5 milliamps nominal, opto-isolated, 15 meters maximum. The isolation is why it never broke. In a stage rig where a dozen boxes plug into different main circuits, an unisolated data link becomes a hum path and a shock hazard. MIDI is one of very few consumer data standards galvanically isolated by design, and that came from the Japanese engineer's second objection. The bill for serial comes due here, 320 microseconds a byte. Send an event on all 16 channels at once, and the last one arrives up to 16 milliseconds late. The industry named the audible result, MIDI slop. Kikumoto's running status lets a sender omit the status byte on consecutive same-type messages. 3 bytes down to 2, a 33% saving, a bandwidth optimization compensating for a rate chosen for cheapness, compromise fixing compromise. Winternam, Anaheim, the 21st to the 23rd of January 1983. A Sequential Prophet 600 was connected to a Roland Jupiter 6, and they played together. Or possibly a Roland JX 3P. Sequential's own museum page said JX 3P, Billboard reported a Jupiter 6, and Kakahashi himself could not later remember which machine it was. The most famous moment in this story, and its principal's accounts diverge. One more detail from that day. Smith arrived late and was initially refused entry by security because he did not have a NAMM pass. The man about to demonstrate the standard that would define the next 40 years could not get into the building. The MIDI 1.0 specification was published in August 1983, 14 pages. By 1995, it was 58 pages plus a 7-page appendix and 13 pages of tables. 14 pages conquered an industry, and what it left out is why. It specified transport and syntax and almost no meaning. Program change 5 meant whatever the receiving instrument's 5th patch happened to be, which made it implementable on an 8-bit micro by any of a dozen firms with competing engineering cultures and left it beyond the reach of obsolescence. A specification that does not describe sound cannot be outdated by new ways of making sound. FM, sampling, wavetables, granular, virtual analog, software instruments, phone apps, all of it fits through a hole designed for analog polysynths. The blank space did have a cost. Roland shipped GS in 1991, Yamaha shipped XG in 1994, competing proprietary supersets of General MIDI from the 2 companies that co-founded the open standard. Cooperation at the transport layer, war at the semantic layer, exactly the layer 1983 left blank. MIDI 2.0 was unveiled in January 2020 after 15 years of research, 16-bit velocity, 32-bit controllers, 256 channels. MIDI 2.0's hardest requirement is not resolution. It is not breaking 1983. Smith's 2 statements about his own standard both true at once. Connect an instrument built in 1983 into one built today, and it works. And at this point, it is somewhat outdated and certainly slow. On why it hasn't been. The trouble is there are way too many entities involved to get agreement. The coordination problem he solved in 1982 now working against him. Kakehashi and Smith received a technical Grammy in February 2013. The MIDI Association marked it with an advertisement listing over 700 companies that had contributed to MIDI's adoption. 700 companies. 0 royalties. 2 months later, Fortune ran a piece about Smith under the headline, "One of tech's most successful inventors never made a cent." The engineers who wanted something better were right. Ethernet was faster. Parallel was faster. 32 bits would have been better than 7. And none of that mattered because the design constraint that won was not performance. It was that nobody could refuse it, which is the uncomfortable part. MIDI 2.0 has 5 core specifications, JSON property exchange, and capability negotiation. It is a better protocol. It also violates the one requirement that made the original win.